A very warm welcome from me for the first Webinar Wednesday. I hope you can all hear me well. I see we have already quite a few participants that joined us today. So let's start with the first Webinar Wednesday, a new global webinar series to showcase latest natural refrigerant trends, technologies, and products. My name is Nina Masonga. I'm Chief Market Development Officer for Shecco, and I'm very, very excited personally to be the one launching this new series that is part of Shecco's market development activities to spread knowledge, connect the right sources, and to ultimately drive the business case for natural refrigerants around the world. One sentence about us: we are a market accelerator for climate-friendly technologies. We have been working with the HVAC and R industry for the last 15 years. We organize events, we operate online platforms, publish magazines, and we do research into market and technology trends. And now we want you to be connected with us on this digital platform. So if you want to get in contact with us for any question or idea you might have, please send us a message at webinar@shecco.com. We are two from Shecco today to take care of you, together with Justina, my colleague from the Brussels office, who will be responsible for all the technical handling in the background and for reviewing your questions. So for this very first Webinar Wednesday, we have more than 400 registered persons, and this already shows the power of this tool, that we can connect continents and individuals that might have not joined at the very same time. So I know that we have quite a few participants from North America, from the US and Canada, but we also have European participants from Africa, and there are Asians and Australians as well, but they might be sleeping right now. So all the recordings from today's session will be sent to you. The link to the recordings will be sent to you shortly after, so you can calmly view them after. So this will be sent to you, as I said. Now, the high number of registrants also more importantly shows that it's a very strong indicator for the interest in CO2 as a refrigerant, especially for food retail solutions. And this is precisely what our first host, leading component supplier Danfoss, will be talking about today. So the session will take around 1 hour with Q&A session included. And I have the pleasure of sharing the session with 3 speakers from Danfoss, taking the floor one after the other, which is first off Jim Knudsen. He's Food Retail Regional Segment Manager for the US, followed by Mark Menzer, who is US Director of Public Affairs. And last off is Kenneth Ben Madsen, Global Application Expert Food Retail from the headquarters, Danfoss headquarters in Denmark. So at the end of each section of each presenter, you have the opportunity to ask questions. And if you want to get the presentation slides, you should directly contact Jim to get the slides. If you want to get in contact with these 3 speakers, you have their contact details at the end, their email addresses, so please don't hesitate. To make this session as interactive as possible, after each presenters, we will have time to allow for a few questions, so don't be shy. Ask your questions at any time you like. We filter them, we will take them to the speakers at the end. And at the very end of the session, we will have a general Q&A as well. So before we get started, just really briefly some housekeeping rules to get you familiar with the tools. So by default, you are all muted, so we cannot see or hear you. We cannot see what you're doing in front of your screen, but you should be able to see and hear us. So if you cannot hear us properly, please check the audio settings, which should be at the top right-hand corner of your screen. There should be a button called Audio Settings to make sure your speakers are on and they are properly working. Next to the audio settings, you have the Q&A, and it's very important because if you click on this tool, you can type in your question. Normally, you would probably have 2 types of questions. A first type of question is to the speakers. So while they are speaking, whenever you feel like you need some clarification to some slides or you have a question to the speaker, please type in your question. We will receive them, and we will then filter them and give them to the speakers after each presenter. And if you have a specific question to a specific speaker, please maybe indicate who you're targeting, if it's Jim, Mark, or Kenneth. And that second type of questions could be technical, so you might have a problem with the system maybe, and that we can reply to you instantly via text message, also using the Q&A tool. Some of you might have a chat, might have a chat function, which is not to be used. We deactivated it because not everybody has that, and we want to really use the Q&A tool for every question you might have. And then some of you might also have the raise hand functionality, and I already saw that some participants use that. This is to basically flag your participation, and if we ask you a question, for example, to raise your hand, then that would be something you can do. So while I change the presentation to the Danfoss slides, maybe we can test this, and you can all raise your hand now. So we see that you fully understood how it works. And my screen is right now filling up with loads of raised hands. Okay, so that means it works. And I can just now switch to the slides. Give me a second, please. So I hope you can all see the Danfoss slides now. This topic of today is advanced CO2 systems, a global approach, and US trends. I said we have 3 speakers. So first off, today is, well, this is the structure, sorry, of today's presentation. So we will learn more about food retail, environmental trends. Then we identify issues, what is worrying for the food retailers. And at the end, we will have some solutions, how we can help. That's all by Danfoss, obviously. So the first speaker I would like to introduce to you is Jim Knudsen. He is Regional Segment Manager for North America for the food retail business and Danfoss. And he's a very experienced refrigeration executive, specialized in developing global marketing, business development, and product strategy. And he holds 5 US patents. So now I'm going to give control to Jim. Over to you now. Justina, I think you have to unmute Jim.
I think, Nina, we are also watching the wrong slides. We are seeing the slideshow you showed first.
Okay, hold on. Let me try again. Better?
Yes.
Yes? Now we see the right slides?
Yes.
Okay. Sorry for that. Jim? Jim, can you hear us?
Can you hear me? Oh,
yes.
There we go.
Yes.
Oh, okay. Can you put the slides back to the first one, or do I need to do that?
Yes, you can do that.
You have a lot more confidence in me than I do. I can't seem to be able to change the slides. I'm going to have to ask you, Nina, to change the slides. Oh, there we go.
Problem. Okay, no problem.
Okay.
I can do it for you. Mm-hmm.
Yeah. Okay. Go back to the first one. Everybody needs to see my picture. Anyways, hello, everyone. Welcome to our Webinar Wednesday. I want to say hello and welcome to all my friends from food retail. I've been in the business for a while, and I know a lot of you, and I know you probably wanted to see my picture again. So if we go to the next slide, Nina. I'm going to talk a little bit about grocery trends. I'm going to spend a lot of time on it. You all know this market very well. In researching this, I looked at a lot of different trend publications, and I think Planet Retail got it pretty right. So I'm using the Planet Retail trends as a reference here. And I think this is a tough business, and I think the trends reflect that. Growth has become increasingly difficult to get, and a lot of it is being eaten up by new players, by value players and discounters, as well as new fresh formats. And this is certainly represented in the strategies of a lot of the big retailers. In addition, consolidation is a really big trend in this industry. And as a matter of fact, I found references to the consolidation trend going back to 1995. So this has been a trend in our industry for 20 years. I know that's not a surprise to you. And you can see some of the changes that have happened over just the last year or so. And I expect that a number of you on the call may have been affected by this. So it's a dynamic business. The big guys are getting bigger, and there's a lot of change in the business for consolidation. Next slide, Nina. The march of the discounters, I think that's an interesting way to put it. The discounters are certainly making an impact on the business. Those new entrants into food retail, like dollar stores and pharmacies and such, as well as the traditional discounters, small limited assortment stores, Save-A-Lot and Aldi. And very soon we'll have another entrant. Lidl is coming into the North American market. So that certainly is taking an impact on the growth of the industry and pricing. And then new formats and business models are emerging. Everybody's chasing the millennials, as I'm sure you know. People are changing are moving to more fresh formats. Target is a good example of that. I also am interested in this new online startup called Jet, which is looking at a subscription model for grocery retailing, something new. And then I'm sure a lot of you have heard of Blue Apron, where they not only deliver groceries to the home, they also add value by providing lessons on how to cook and turning people into celebrity chefs in their own kitchens. The next slide, Nina. Thank you. And then the big trend of online grocery. It certainly had gotten a lot of press, and a lot of people talk about it. Over 2/3 of the grocery retailers either are developing an online channel or are planning on developing an online channel. There's a lot of different models, click and collect, home delivery, but it's still a fragmented, growing part of the business. As a matter of fact, less than 2% of groceries are currently bought through the online channel, and a lot less than 2%. So it's still at its infancies, but this particular part of the industry, I liken it to what happened in the restaurant business when quick serve emerged. It's going to be a big part of the industry, and everybody is aware of that. Next slide, please. So with this complex competitive business, why are we talking about refrigeration? Other than Danfoss is a refrigeration company, and it's very interesting to us, but why do we talk about it? And in reference to that, I brought up the FMI worry list. This comes from a publication FMI does called the Grocery Industry Speaks, and these are the concerns that have been voiced by the executives of food retailers. And a lot of these, or a number of these, reflect on refrigeration. State, local, and national government regulations are on the list, very high on the list. As a matter of fact, more concern to grocery executives than competition. Also, energy cost has been on the list for a while, and lately has been growing in importance. And then environmental concerns continues to grow year in and year out as an important area of concern for executives. Next slide. So how do we address these worries? Regulation, energy costs, environmental concerns all point to refrigeration. And so how do we address them? There's a number of different ways. The continuing evolving chemical refrigerant choices are one way. We've been through 4 generations of these, and it's reasonable to expect there's going to be another 2 or 3 before we're through this process. So it is possible that some large retailers will have up to 7 different refrigerants represented in their chains, maybe even more. Also, there's hydrocarbons, particularly for small self-contained applications. Certainly, we're aware of the flammability and the regulations and safety concerns need to be addressed, taken into account in order to address this. And then there's CO2 for large retail. It is the established choice in Europe, and it's evolving in North America as well. There continues to be concerns about the first cost of the systems remaining a challenge. We need an infrastructure of trained technicians, and there's the issue of warm climates, particularly in North America, because North America has more people in warmer climates than they do in Europe. So, and that's going to be the sort of the topic of this presentation. Looking at the CO2 industry, number of critical systems from 2011 to 2016. This data comes from Shecco, as well as Planet Retail for the number of outlets. And you can see that the growth in North America is on the upward slope. By the end of 2016, I expect we'll have 300 to 350 transcritical systems in North America. Compare that, though, with Europe, which has about 6,000 installations now and could be as high as 9,000 by 2016. The relative size of the markets are similar, so the journey is just beginning here in North America, but it's well established in Europe. Next slide. So I put up this infographic. This is a Danfoss infographic. You can get it on our website. And it talks about the 3 trends favoring CO2. A, certainly regulation, and that's on the worry list, and we're going to talk about that. B, which is warm climates. That's what Kenneth is here to talk about. And then C, efficient heat reclaim. We're going to save that for a future webinar, so keep your eyes open for that one. With that, we'll open it up for questions. Nina?
Sure. So let's get some questions in. I hope that we got some, Justina, and we have some here. Yes.
Okay, so actually we don't have any questions for you, Jim, now, but all participants can type the questions in, or actually you can also raise your hand if you want to ask your question live. So please feel free to do that. Yes, but for the moment we don't have any question.
But
well, let's move on.
Hold on, Jem. I have actually a question to you, if you don't mind.
Okay.
You mentioned a few trends for food retail, which I think are really important and interesting. So what struck me there on your slide was the move to online retailing. How do you think that will influence the refrigeration business? Do you see more of the home delivery? Do you see more the transport becoming of importance, or the food storage and the preservation of food? Is that going to be having a different approach or influence on refrigeration?
Well, of course, the story is still yet to be told on that, and so there is an opportunity for some transport refrigeration right now. Typically, the groceries that are transported for home delivery can be in refrigerated trucks, but aren't always in refrigerated trucks. There's also the opportunity for refrigerated drop-off points. These locker systems. For drop-off points for groceries, as well as the grocery venue itself. Today, a lot of online grocery is serviced through existing grocery stores, but there are models, particularly in Europe, where there's such a thing as dark grocery stores, where there's just equipment picking the groceries, and then the customers come and click and collect, and really have no opportunity to go into the grocery store. So I think the story is yet to be told there. Certainly, there probably will be an opportunity for more warehousing, but how else it's going to affect refrigeration, I can't guess.
Okay.
Okay, so I see that we are getting some more questions, so I'm gonna read some of these questions for you. So the first question, Bruce Tarrant is asking, how does the transcritical system operate over 95 degrees?
Kenneth will talk about that later on in the presentation, so I won't steal his thunder.
Okay, then. Next question is, what is the typical size of the systems you are referring to in North America?
Well, in North America, there's a lot of different sizes, but in general, the systems we talk about are for what we would call supermarkets, which is anywhere from 40 to 60,000 square foot systems. So exactly what the BTUs are, I don't have that on the tip of my tongue, but they're large systems when I talk about food retail with regard to the systems here.
Okay, we have another question from Ken Gleason. Jim, you mentioned that in Europe the trend was towards CO2, but what about Southern European countries, which see higher temperatures?
Mm-hmm. They do, but still, in general, the temperatures are even warmer in North America, and that's a big question: is what do you do about warm climates? And that's why we're having this webinar, because it's an issue that we've been working on at Danfoss, and I think we have some technologies that will be interesting. So again, everybody wants to hear Kenneth, so I think we'll let him give his presentation after Mark talks a little bit about regulation, which is high on the worry list, and so we thought we needed to address it.
Okay, then I think we had some more questions, but we can keep them to the end. I want to give Mark and Kenneth the opportunity to go through their presentation as well. So I don't know if you prefer. We can try the remote again, Mark. If that doesn't work, we go with the same system as just now. I gave you the control. You can try. Yes. So just to introduce Mark here, he's Director of Public Affairs at Danfoss. He's a member of ASHRAE, and he has a BS and a Master in Mechanical Engineering. He has an extensive background in the HVAC&R industry and has served on the management committee of the International Institute of Refrigeration. He was also regional VP at third-party testing laboratories Intertech. And last not least, he was Executive VP for the Air Conditioning, Heating and Refrigeration Institute. So over to Mark now.
Very good. Thank you. So let's just talk about the regulatory framework that is making all of this happen. I think you can envision some national or regional programs that are having over that a global treaty. And that is certainly what we're looking for. But in actuality, we have these national programs now in effect while a global treaty is still being negotiated. And we have several regional or national programs, one of those, of course, being the European F-gas regulation, which was passed in 2006. The European F-gas rule reduces significantly the amount of fluorocarbons that are sold in the EU and phases them down dramatically, as is shown here, to about a fifth of 2014 sales by the year 2030. And we'll talk about that phase down in just some more in just a moment. And as of January 2022, refrigerants with a GWP of greater than 150 banned in large supermarket systems. So, of course, that's all of the traditional refrigerants that have been used in recent years. In Japan, they also have an F-gas directive that went into effect last year, and they have a target of 1,500 GWP by 2025. Again, the traditional gases that we use there are being phased down and phased out. And here in the US, we have our SNAP program, our Significant Alternative Refrigerants policy. And that's the mechanism by which EPA manages the phase down of HFCs. It too has a profound effect on supermarket systems. So EPA has a series of notices and rules. A notice is an instrument by which they just say that something is acceptable to be used, and a rule is something that says it's either not acceptable or it's only acceptable in certain limited applications. So in 2009, EPA said that CO2 was acceptable as a refrigerant, specifically in retail food refrigeration and cold storage warehouses. So CO2 became one of the possible refrigerants to use. In 2012, EPA said that hydrocarbons, certain hydrocarbon refrigerants, could be used in small applications up to 150 grams per refrigerant loop. So that just really is for a small part of a larger display case or for a standalone unit. It's kind of limited applications there. Recently, and this is an eye test, but you'll be able to get this slide later if you want it. This EPA said these are unacceptable refrigerants for the uses shown here, including supermarket systems and standalone refrigeration systems. And all of these refrigerants, which are HCFCs or HFCs, are unacceptable. If we look at it in terms of their GWP, you see everything that's red here is now going to be unacceptable, leaving those on the right as acceptable fluorocarbons. And then, of course, CO2, which you couldn't even see the bar because its GWP is only one, is one as well. And that's as of 2017. Just recently, there's been a proposed Rule 21, which further restricts the use of HFCs in certain retail refrigeration. So HFCs are going away, most HFCs, for retail refrigeration purposes. And, you know, not to be undone, California has its own set of recommendations. They've just been released by the California Air Resources Board. These restrictions would be even more strict than EPA's restriction. There's legislation now being passed to put this, make this into a regulation. There's some incentive programs for conversions, but there's not much money in them. So we're watching California, which may have even a more strict phase-out program than EPA as a whole. Very quickly, there's a lot, you know, what effect will the Montreal Protocol have once it's agreed to, and we hope that it will be agreed to this year. Well, there's many proposals as shown here, but when you really get it down to the two big ones, the proposal from the EU and the proposal from North America, they actually look quite similar. And we see a significant phase down on the use of HFCs here in around 2020. And that's the time that is certainly within the planning horizon of most supermarkets. And so how will the Montreal Protocol affect it? Well, I said there's no agreement yet reached. We are getting closer. Some of the issues that we had with the Montreal Protocol have been recently addressed, but there's more meetings this year. We expect it to be passed, and we know that the EPA SNAP rules have been written with the Montreal Protocol in mind. So once we have a Montreal Protocol, that really probably won't have any effect on the existing rules here in the United States. You know, some people say, well, with a change of administration, what happens? Well, the SNAP rules were written by EPA under the authority of Congress. A new president could slow the progress of future rules, but would not be able to unilaterally undo the old rules. We would expect the Democratic president to likely continue the Obama initiatives. And the Montreal Protocol is going to be revisited every few years, and probably the phase out strengthened and accelerated. Of quick review of some of the regulatory underpinnings.
Okay, thanks a lot, Mark. Justina, do we have some questions for Mark?
Yes, we have two questions for you, Mark. So Ashley Murphy is asking, which hydrocarbon refrigerants are acceptable?
For retail refrigeration, propane, with, as I said, large use restrictions, particularly the 150 gram limit here in the United States.
Okay, thank you. And another question from William Buckingham. How is the industry in the US catering for the training of engineers in relation to the increased working pressures? In the UK, for example, this was considered as one of the initial restrictive issues facing the industry and held some end users back from going forward with CO2 systems.
Yeah, certainly the training of technicians for the flammable refrigerants, the mildly flammable refrigerants, the high pressure refrigerants are very important and going to have to be addressed and starting to be addressed by the manufacturers as they roll out new equipment.
Okay, thank you. And another question is from Yuda Mendes. She's asking, what will happen with R32?
So R32 is a component of some blends, and if those blends meet the GWP requirements, 32 will still be around as part of those blends. Pure 32 in the US has been permitted in very small systems, now window air conditioning units, but not pure 32 for refrigeration purposes.
Okay, thank you very much. And another question is SNAP rules applying to Canada supermarkets?
So Canada has just proposed its own set of regulations, but it is very close to the US SNAP rules, and I know the Canadian government is working closely with the EPA to make sure that those rules stay pretty much consistent.
And Anil Kumar Yadav is asking, will 410A refrigerant also be used for refrigeration?
So I think 410A as a pure refrigerant, and maybe Kenneth can speak to this as well, I believe it probably has a too high a GWP level to be used as a pure refrigerant or as a refrigerant, as a blend.
Okay, another question from Ken Gleason. R404A has been replaced by R452A with GWP less than 2000 and similar series refrigerants. What do you think is the life of these in terms of being banned?
Yeah, I mean, that would be speculation. As I said, the Montreal Protocol will be revisited. I expect it'll be strengthened and the timelines accelerated. You know, that's why today, for instance, we're talking about a very low, almost zero GWP refrigerant.
Okay, thank you very much. And I don't know if anyone, okay, we have another question. How to reduce the cost of equipment cooler for Coke?
Okay, well, you know, reducing the cost of this equipment is certainly one of the manufacturer's constant concerns. And that's not the kind of thing that I'm doing, but again, maybe we'll get into that later on in the presentation.
Okay, before we move on, I might have like one more question, then we keep the other questions to the end, because I see that people really liked your presentation. You get so many questions here. So just a question maybe from my side as well. You talked about California's targets, which are very, very ambitious, maybe even more ambitious than the EU F-gas regulation and certainly stricter than the current EPA rules. So do you think that will have an impact on the other US states anytime soon? And the second question here is, do you feel that Danfoss is ready to support this push should it come?
Well, look, it really makes sense for the U.S. to have a unified rule for refrigerants as we do for efficiencies of equipment. And I would hope that we would be able to agree on just one set of rules and be able to produce and distribute equipment that way.
Okay. Well, thanks. Yes, there are more questions. We keep them to the end. So let's just continue with Canet here. Let me just take over the control. Canet, yes, so he's global application expert for food retail from Danfoss in Denmark. He has a BCE in mechanical engineering from Denmark, and from 2001 to 2008, he worked for the Danish Technological Institute, DTI, which is one of the most well-known research institutes in Europe when it comes to refrigeration. He worked there in the heat pump and refrigeration section, focusing on food retail. So he can tell you all about the technology side of it. Over to you.
Thank you, Nina. I hope you can hear me. So the agenda for my talk today is we'll go through the different technologies that we start to see coming on CO2. So the most well-known is transcritical booster systems, where we have around 7,000 in operation right now, and this is a technology that we are rolling out commercially available. What we see with this technology, and this is what we all think of when we talk about transcritical CO2, is that we have, let's say, a limit. If we reach something like the 80 degree Fahrenheit or something like that, then we start to lose efficiency, and then we cannot, let's say, claim that we are more efficient than 404A. And 404A on energy efficiency is, let's say, at least my benchmark, because that is the one that we all know. So we have known for some time that if we want to take, let's say, move this or remove this CO2 equator that everybody is talking about as well, then we need to do something about the technology. And one of the things we're doing is working with parallel compression. Here we have around 1,000 systems in operation, and this is also commercially available. And we see this picking up quite significantly here in Europe, and that is mainly due to Southern Europe stepping into the CO2 transcritical market. But we still want to have more efficiency, because parallel compression at around 100 degrees Fahrenheit, we start to, let's say, consume more energy than 404A. So parallel compression is basically a solution that will give you, in just about any climate, it will give you an annual lower energy consumption than 404A. But you still have the very warm periods where the peak energy consumption is higher. And that is where we start to implement ejectors. This is not a product that is commercially available. We are working with a handful of selected OEMs, but they basically have access to this technology as any other components from Danfoss. With ejector technology in the system, there you will actually have an energy consumption that at all times will be lower than 404A in any climate. Come back to all of this later on in the slides. And then, let's say, the last step we have chosen to talk about today is that we want to go flooded as well. And I'll get back to how we do that a little bit later. But we have 5 systems in operation, and we are currently in a testing phase here. But that will also give a significant energy improvement. So what I'll do is I'll step through the different systems, and I'll start through with the booster system. So we have been installing booster systems here in Europe since 2006 with this concept, and there have been, let's say, other concepts before that. Today we are having around 7,000 systems, as I just told you before, and this is what we consider being the standard system. Later on in the presentation, I'll show you some charts about energy consumption and about swept volume. When we talk about swept volume, so that means compressor capacity basically, there I'll use the booster system as index 100. So that would be my reference. When we talk about energy consumption, I'll use 404A as my reference for energy consumption. And when we talk about energy consumption, we are only talking about MT, not LT. Because in the way I see it is that LT is basically just let's say an empty evaporator with a very high superheat. So to take that out of the equation, I've decided not to look at that, but only to look at the MT. Even though CO2 actually has some advantages over 404A in the low temperature region. Oops. If we should just go through the diagram, you can see the compressors, the MT compressors up here. They lift the pressure from our MT suction, which is the blue line, to the red line here, which is our high pressure. And this is where we have the high pressure in the system. And now you have to excuse me for being European, but I'm best at bars here. So the design pressure here is usually around 120 bar, and it's, let's say, the trend is that we move up towards 130 bar. All our components are designed for 140 bar. But you can see the high pressure side is only the red line, so that means it's from the compressors through the gas cooler and to the expansion valve again. So none of this high pressure CO2 is inside the store. All of it is kept in the machinery room and outside the building. So that minimizes the risk of, let's say, high pressure incidents significantly. After the high pressure valve here, we go into our receiver here, where after the valve here we have a mixture of gas and liquid, where roughly 50% of it is gas, roughly 50% is liquid. The gas we send through the gas bypass valve here to keep the receiver pressure relatively low. So a receiver pressure around 35 to 40 bar is quite normal in normal operation. So the gas we send over here to the MT compressors, and the liquid we send through the liquid line to expansion valves, and we run a dry expansion here, so we have a superheated gas that goes back to the compressors here. On the LT side, we take the liquid out, again, expand it in the expansion valve here, have a dry suction line to the LT compressor that boosts the pressure from the LT suction pressure to MT. So that's basically how the system operates and works. This one we'll skip. This slide here, on this diagram here, you'll see a few times. So on the x-axis you have temperature in Fahrenheit, and on the y-axis you have energy consumption relative to 404A. So that means that we are crossing here at something like 81 or 82 Fahrenheit. That means that we are, let's say, break even with 404A. If you go for higher temperatures, you can see that the energy consumption is higher. So, of course, moving into warm climates, this is something we need to address. First step on this is that we want to do parallel compression. So we take out roughly half of the compressor capacity here on MT and put some of it back here on parallel compression. And here we also have a saving in swept volume. I'll come back to that later. So here we'll actually reduce the number of compressors and thereby reducing the first costs. So this technology here applies mainly to systems above 100 kilowatts. Smaller than that, we are working with another technology where we can get the same benefits, more or less, but that is a little bit further out. But basically we are chasing the efficiency gain. So to understand what is happening here is that if we have, let's say, 100% mass flow through our gas cooler, then we go through our high pressure expansion device. In this case here, it will be a valve, but it could just as well be an ejector, which we'll go back to later. Instead of sending the 45% of gas through the gas bypass valve to the MT compressors, then the 45% gas will be taken care of by the parallel compressors here. And the rest, the 55%, will go into the evaporators, evaporate, and return to the MT evaporators, or MT compressors, sorry. The efficiency gain we get here is that instead of operating all of our compressors at the MT suction pressure, then we increase the suction pressure by something like 10, 12 bar for 45% of the mass flow. And the higher suction pressure here is actually where we pick up the energy efficiency of the compressors, because they're running with a higher suction pressure. And as well, since they're running with a higher suction pressure, they can also move more capacity with the same sweat volume. So there we get a saving in sweat volume. Same graph as I showed you before. Last time we were crossing at 82 with the booster system. With the parallel compression system, we moved that up to around 101 Fahrenheit. So that's a significant improvement, and you can also see that the difference, even at higher temperatures, is below 5%. So that means that annually you will have an energy consumption that is on the same level or lower than 404A. It will be lower, actually. If you look at this graph here, which is new, then you have the ambient temperature here in Fahrenheit, and on the y-axis here you have the relative saving in sweat volume compared to a booster system. So this is basically first cost saving here. So at 105 Fahrenheit, for instance, you would have something like an 18% saving in sweat volume. So that, of course, equates into a saving in cost as well. Next step for us is to introduce ejectors. And what the ejector does is that it takes gas from the empty side here, moves it through the ejector into the receiver here, where we have the parallel compressor that takes the gas. So basically how the ejector works is that it takes load from empty, the ejector compresses the gas and moves it to the parallel compression. So we are basically enhancing our efficiency of the parallel compressor by giving it more gas to work with, moving load from empty to parallel compressor. So that is what ejectors or gas ejectors is all about. We have had the first systems in operation since 2013, which is not with our ejector, and we have had our own multi-ejector in operation since January 2015. And the results I show here, they are based on simulations, but it actually equates quite well into what we have seen in real life. Again, if we take the same drawing as before, then you can see we have 100% going through the gas cooler into the ejector here. The ejector is then taking some gas from the empty side here. It's taking around 35% of the total mass flow is being entrained in the ejector. So that means we are lifting 35% of the mass flow away from the empty compressors into the ejector, into the receiver, and then the parallel compressor will do the compression. So instead of with the booster system, we had 100% mass flow here through the empty compressors. If we use parallel compression and ejectors, then we do 20% with the empty compressor. We do 80% of the mass flow with the parallel compressors, and that is what is giving us an energy saving here. If you look at the chart here, then I have two different lines. I have one with an ejector efficiency of 25%, and I have one with 35%. The peak efficiency of our ejector is 38%, which is, to my knowledge, the highest recorded efficiency on a CO2 ejector. 80% of the measuring points we have are between these two lines. So my best guess is that if you should accumulate your energy consumption from these data here, it would be somewhere between these two lines. So if we compare to 404A, then the most interesting thing is that you can see that we are always below 404A in any temperature. So this is giving us the energy saving that we need to have in warm climates. If we look at sweat volume, again you see the two graphs. Since we are doing more of the duty with the parallel compressor at a higher suction pressure, that of course equates into a saving in tread volume. So again, if we choose the 105, then a saving of, let's say, 25% compressor capacity is not unrealistic, which is of course giving you a saving in first cost. The last step of the way, and you can see there is a line missing, but I'll come back to that later, is to combine gas ejectors and liquid ejectors. So what we'll do here in this system here is that we will operate the empty expansion valve here not as a superheat control, but operate it with a very, very low superheat here, so that we actually get liquid out. The benefits of that is, of course, we utilize more of the evaporator. That's one thing. But in part load, we also get the bonus that our superheat is actually not the one determining the temperature difference of the evaporator. So by removing the superheat, we can actually run with a smaller temperature difference. And that way we can higher the suction pressure of the MT compressors and get a higher energy consumption. And what we see in average is something like a 5 Kelvin higher suction pressure for the MT compressors in average over the year. And here you'll actually get the bigger saving in wintertime, a little bit smaller saving in summertime, because part load conditions is what we're optimizing for. When the liquid comes out of the evaporator, it goes into the, let's say, suction accumulator here, where we separate gas and liquid. The gas is taken from the top here and put into the MT compressors here, and that's the line missing. The liquid and the gas is then being taken from the bottom of the receiver or suction accumulator here and put into the ejector here. By doing this, we remove the excess liquid we have from the evaporators and the gas at the same time with the ejector. Put it up here, the liquid will then take another round in the circle, and the gas will go directly into the parallel compressor. So here we are basically combining two things in the same system. This is something we are still testing. We have more or less the equipment to do it, but it's more control algorithms and so on we are testing now. If you look at energy savings, then it's more difficult because here load is also a parameter. But my best guess is that it will look something like this, that we will get something in warm temperatures, we'll get something like 10 to 20% saving in energy consumption with both gas and liquid ejectors in, compared to 404A. And since we are running a higher suction pressure, we also get a significant saving in tread volume. So just to summarize this, I have two slides. I have one for, I have two different temperatures. This is 110 degree Fahrenheit, and you can see the booster system. If we compare energy to 404A, we are 25% behind. And if we add parallel compression, that changes the picture quite a lot. If we go for gas ejectors, we get a little bit more efficiency out of it, and if we combine it with liquid and gas ejectors, we get a little bit more again. If you look at tread volume, there are also some significant savings, so we believe that maybe we can save up to 1/3 of the compressors by implementing both gas and liquid ejectors together with parallel compression. All of these, well, you can see in 2 or 3 years, more or less, we have moved the CO2 equator from up here and then all the way down here. So it's actually a significant energy savings we have achieved in the last couple of years. Here's the same picture, just done at 90 degree Fahrenheit. So that the savings are not as big, but still significant savings. But basically what we are coming with here is a solution that would work both in a cold climate and a warm climate. The ejector will not be active in cold climates, but it will be active in warm climates. In cold climates, it would just act as a let's say, an expansion device. So to summarize or to round off, every retailer needs some kind of a long-term strategy for refrigeration. And from Danfoss, we would like to welcome you to work with us, and we would like to share our expertise and knowledge on this. So please feel free to contact us if you have any questions. That's it from my side, Nina.
Okay, thanks. Let's take this over. Let's put the last slide up so people can see how to contact you. I think we're here. Yes. Okay, let's take this up again. So, Justina, I saw that there were many questions. So we're running a little bit late, of course, but I think it's worth it because there were so many questions, and that's precisely why we're doing this webinar. So, Justina, go ahead.
Okay, Kenneth. So we have several questions for you. Dinesh Yoshi is asking, which system will you advise for 1 ton refrigeration system working above 40 degrees Celsius ambient?
Yeah, and I need a little bit of help, because what is 1 ton in kilowatts? I'm a little bit too European for that. So if somebody can help us on that, then maybe we can save it for later, then write it in the Q&A.
Okay, maybe then I can ask another question. Okay, so Anil Kumar is saying that 3.5 kilowatt.
Okay, 3.5 kilowatt is not a lot. So then we are down in, let's say, bottle cooler size. And that is not the area that I'm working the most with. But it would be possible to implement ejectors in that type of systems as well. The system will be different from what I've seen today. That's what I can say. But we also have solutions for that. We don't have the ejector components for it. Or maybe we actually do. But it will be significantly different from what I've seen today or what I've showed today. But we have a solution for it as well.
Okay, thank you. Javier Duarte is asking, have Danfoss tested CO2 systems with lower condensation temperatures from water chiller excess in other systems? For example, from a CCHP cogeneration system?
Not exactly in that combination, but we have tested it with cold water from a chiller. And the thing is that if you use the cold water from a chiller, then you, let's say, remove the effect of parallel compression and ejectors, because you are not having any expansion work and you're not having any gas that you can compress from your receiver. So from that point of view, you are basically talking about two competing technologies. And we have chosen this path here, but we have systems in operation in Spain where we have used this. And it is a little bit so-so if you choose one or the other. But it seems like the market has chosen not to go with the solution where they use cold water with a chiller. The reasons for it, I could imagine, and I can only guess, is that the first cost is higher. Unless, of course, you have the chiller.
Okay, thanks, Kenneth. Another question from Ken Gleason. You showed earlier that for systems smaller than 100 kilowatt, parallel compression was not an option. Does this then mean that for systems smaller than 100 kilowatt, CO2 systems will always be less efficient than R404A systems?
No, that's not the case. We are working, and we also have systems out running that are smaller than 100 kilowatts, and basically you can build them with the technologies I've showed here. But the first cost is, I would say, too high. But we are working on another concept where we are using a more simplified system where we can get almost the same benefits as what I've shown here for a lower cost in the small sizes.
Okay, thank you. Another question from Ashley Murphy. She's asking what type of heat exchangers are used in these CO2 systems, both transcritical and subcritical?
Well, if we're talking about the evaporators, they're not that different. It's smaller tubes normally in the evaporators, but that's it. In the gas, as gas coolers or condensers, it's the same type as you're using on H2Cs. You can both get let's say one where you have water on, and you can get the dry ones. The dry ones are probably the most common here in Europe. If we're talking about cascade heat exchangers, it's standard, more or less, cascade heat exchangers for cascade systems, but for the high pressure, for 120 bar for heat recovery, you need to use heat exchangers that are, let's say, suitable for it. In the past, we were also using shell and tube heat exchangers for the heat recovery, but the price is simply too high, and the efficiency is not good enough compared to what you pay, of course.
Okay, thank you. Another question from Derek Tips. Would you design the main MT compressors to include flash gas load in case the dedicated flash gas compressors fail?
No, we are not doing that. Normally, it's not different from a normal system where you design, because if you have 4 compressors and one of them is not working, then you lose 25% capacity, and the same goes here. But what we do is that we have a possibility to do, if the parallel compressors is only, let's say, 50% of the installed capacity because one is broken and we have 2 compressors, then we have some possibilities to maneuver around it and get more capacity out. But we can, of course, not, it's not magic, so we cannot get the 100% capacity.
Another question from Paulo Uccello. Are ejector systems already installed in US or Canada?
We have some in operation in labs, but we don't have any in the field yet in the US and Canada.
Okay. Another question. Have you ever considered using shell and plate heat exchangers for these CO2 systems instead of shell and tube? They are more compact and more efficient than shell and tube heat exchangers, Ashley Murphy says.
Yeah, that could very well be. Now, we are not in this business here of the high pressure plate heat exchangers, so it's not, let's say, within our normal working area. But the only thing I can say is that the main part of what I see is plate heat exchangers. We see from time to time plate and shell, but it's very rare.
Okay, next question from Arun Kumar. Who are the CO2 compressor suppliers, especially for coke, except Sanden suppliers?
That's a good question. I only know of Sanden in that size.
Okay. Next question. How can one eliminate the risk of dry ice formation?
Well, the only way you can eliminate it is to keep the pressure high enough. Dry ice is not something we see in operation. And if you have dry ice when the system is in operation, then we are actually so lucky that dry ice is taking less volume than the liquid. So that means you will not have any problems with bursted pipes because of frost or because of dry ice. But usually the only situation where we see dry ice as an issue is if we have safety valves blowing from liquid. And there I must say we have never seen problems with blocking of safety valves. And then we see it when we empty the system. And then the important thing when you empty the system is always to remove the liquid first and then take the gas afterwards.
Okay, thank you. Next question from Stefan Moore. Are the same Danfoss CO2 control solutions that are sold in the EU available for sale in NAM?
Yes, we are running exactly the same program in North America that we are using in Europe, so no difference there.
Another question from Paolo Uccello. Except stainless steel, do you have other material for piping high-pressure equipments?
We are using stainless steel, as I said, but we are also using black steel, and we also see this K65 alloy taking more and more of the market. So that's the three options you have. So.
Another question from Arun Kumar. Why Danfoss is not developing CO2 compressors for coke equipment?
Well, that's a long story, but we actually did that at some point, but we sold off the development.
Yes, Tina?
Yes.
I think we had some questions also for Mark, so we can maybe have a bit more balance.
Okay, let me see.
I did see a question earlier about the Montreal Protocol that I can address.
Sure, go ahead.
Yeah, I think the question was, I said that since the SNAP regulations have been written with the Montreal Protocol in mind, does that mean that the SNAP regulations now are all we're going to see? And I think the answer to that is clearly no, that the SNAP regulations will continue to drive down GWP of refrigerants. Not all applications have been addressed yet, and perhaps even for some of those applications that have been addressed, we could see further SNAP rules in future years. So no, we will continue to see SNAP rules driving down GWP of refrigerants.
Okay, thanks, Justina. Any more regulatory questions there?
Yes, just checking. Maybe yes, Mark, another question for you. Do you think that cascade ammonia CO2 is a good alternative of traditional refrigeration system in hot climates?
Okay, so that I really have to put that one back to Kenneth. He's our technical guru there.
Yeah, no, we haven't been talking that much about cascade systems today, but ammonia CO2 cascade systems are, from an efficiency point of view, probably one of the best solutions you can find. And there we will have a very difficult time competing on energy with that solution. The main well, the reason why the market is probably not going in that direction for, let's say, in bigger numbers is that ammonia is a little bit difficult to handle, and there are many places where you're not allowed to bring in ammonia. But from an efficiency point of view, ammonia is a fantastic refrigerant.
Okay, thank you. And another question I saw was for Jim.
Mm-hmm. Excuse me. We've talked a couple of times about first cost, and I just want to talk about that a little bit. As I see it, the reasons why the first cost of the transcritical systems are so much higher than traditional systems in the U.S. are there are three aspects. First, volume. In Europe, they're making 20 times the volume we have in the U.S. So that certainly affects cost. And you can't use the same components in Europe as the U.S. because standards are different. So harmonization of standards would help that. Secondly, of course, the pressures are higher. So there's a certain amount of cost that's associated with that versus 404A. And then lastly, there are some control components and efficiency generating technologies that are used on CO2 that could also be used on HFCs that raise the cost of the CO2 system, the apparent cost of the CO2 system. And one specifically is case controllers. In Europe, it's standard both on HFC systems and CO2 systems to use case controllers. So that's not seen as a CO2 cost. Whereas in the US, just today, in today's market, people are starting to realize the efficiencies that case controllers can bring to you. So we're seeing more and more people putting those on HFC systems as well. But those are the three aspects that I see most affecting the first cost of CO2 transcritical systems.
There was a question earlier, I can see here, that is asking, do you have any predictions or data about sales of CO2 in India or Asia? So apparently someone more active in that area. So what is your business there in Asia and India? And what are your targets? How's the market moving for Danfoss?
Well, I'm specifically responsible for North America, but I am a little bit aware of what's happening. Right now, there's a lot of test systems going on in Asia and Africa. We've done, Kenneth himself can talk about some South African systems that we've done. But in general, the developed countries are leading the way in terms of regulations, and so that's where the biggest push for natural refrigerants, specifically CO2, is. But it's certainly being tested in all regions.
Okay, and we have a question here that probably is good for both Jim and Mark. What's the major reason that North America is still using HFC and are not switched to natural refrigerants?
I think that's cost. And, you know, some of the things I talked about with regard to cost, the fact that the HFC systems are a little simpler in North America and not as efficient as they have been in the past in Europe. We're now catching up on that as well. So the cost difference between CO2 and HFC systems is coming down.
Okay. If I can do an interpretation of a question here, do you believe that CO2 is going to cover the different applications like for transcritical and subcritical systems, or do you think there's going to be new alternatives coming up? What's your long-term strategy on this one?
We at Danfoss, you know, support all low GWP solutions. So we have solutions that work with chemical refrigerants as well as natural refrigerants. For large food retail systems right now, from my point of view, it's really hard to beat the simplicity of CO2 as a refrigerant. And as the costs come down, I see that as being probably a similar path that they've followed in Europe in terms of the deployment.
And David Taylor wants to specifically know if you think that subcritical CO2 systems will be a consideration for North America when it comes to higher ambient temperatures.
Subcritical systems for higher ambient temperatures. There's always the ammonia system, which is very efficient. And maybe let Kenneth answer this one.
Yeah, but it's not an easy question to answer, because basically here we are talking about what will be the winning technology, if it will be transcritical or cascade systems. And what we can see here in Europe is that in Southern Europe it has been cascade systems up till now, but transcritical systems is rapidly eating away of that market. And I could imagine that the same will happen in other places. We see a very, very big interest from warmer climates. So I guess from my point of view, I would say that transcritical could very easily take a large part of that market, but in reality, it will be several different technologies living alongside each other for many years.
How do you see the topic of condensing units for the United States? Do you think this will be used by food retailers more and more? How do you see that coming?
When we say condensing units, it could be semi-plug-in that is meant. And I think in some store formats, a semi-plug-in fits in very well. Where in other store formats, it's not fitting in that well. And on energy, I think it's not the best solution, but you get some other benefits with semi-plugins.
I think we had a similar question before about training. What are you specifically doing in Danfoss supporting industry technicians and students becoming more proficient? Do you have some educational systems, or do you have some training programs? What's happening?
Yeah, well, we have some e-learning lessons, so you can sign up from our website, and there are a lot of e-learnings on CO2, especially different modules you can attend on different levels. And then what we do is we do specific training with the different customers we have. So that is something we do tailor-made for each customer.
Okay, maybe a tricky question. I don't know if you can answer that here. Someone is asking, Paolo Ocayo is asking about the cost difference between a standard system and a CO2 system, and he's referring to 404A and 407A.
That is a very difficult question to answer. And I think there are more things in it to be able to give a good answer. But if we're, let's say, trying to compare apples to apples, so that means that we are using electronic expansion valves on both systems, and we are in a mature market where CO2 has been for, let's say, a longer period, then the difference is not so big. In UK, they actually claim to have cost parity. So the CO2 system is more or less the same price as the 404A system.
Okay, there's constantly coming questions, so I think we have to just end at some point, but maybe another question for Mark here specifically was that there's talk of another revision of the F-gas. So any information on your side regarding timelines on this? When will the technical content be known, and when will it become law?
Well, I mean, the F-gas regulation was updated not very long ago, and some of it just came into effect. And I don't know about any updates, but if you just look at the regulation now, it's a very long-term regulation, and I think you can kind of see the path that the European refrigerants are going to go in for some time in the future.
Okay. Yes, and I think there's 22 open questions for you. I think what we can do is we can send them to you, so you can have a look and reply if you want. We had some questions as well if the presentation will be shared, not the presentation as such. If you want to have the presentation slides, please contact Jim for this specifically. Yes, again, Jim. And the recordings, obviously, because we recorded this session, so we will just put that in the right format, and we'll send you a link in the next few days so you can watch it calmly at home or share that with your colleagues. Thank you very much for your attention. If there are any final words from any of the participants, feel free. No? Okay.
Just thank you all for attending.
Yes, that's obviously the most important. Yes, so any question you might have to webinar@shecco.com or contact Danfoss directly. Thank you for attending, and hope to see you soon for next Webinar Wednesday session. Bye. Bye to all.